Welcome to a lesson on spherical coordinates. The goals of this video are to define spherical coordinates and also to convert between spherical and rectangular coordinates. In a spherical coordinate system, a point in space is represented by an ordered triple where the first coordinate is rho, and rho is the distance between the point and the origin. The second coordinate is theta. Theta is the angle counterclockwise from the polar or positive x-axis in the xy plane. This is the same for cylindrical coordinates. And the last coordinate is phi, where phi is the angle between the positive z-axis and the point. So if we have this point P here in space, the length of this red segment would be rho. This angle here would be theta in the xy plane, and this angle here, phi, would be the angle between this segment here in red and the positive z-axis. Let's take a look at an animation to get a better feel for this. Watch as I increase rho, this point increases in distance from the origin. Now I'm going to increase phi, the third coordinate. Notice the angle between the z-axis and that gray segment increases. And as I increase theta, it rotates from the polar axis or the positive x-axis counterclockwise. And now you can see why they're called spherical coordinates. Any point using spherical coordinates could be viewed as a point on the surface of a sphere. Here's that point in space. Now we can use the following equations to convert between spherical and rectangular coordinates. And as you can see, most of these come from using trigonometry, or in this case here, this comes from the equation of a sphere. These three equations are often helpful to convert from spherical to rectangular coordinates, and these three equations are helpful when converting from rectangular to spherical coordinates. Let's go ahead and take a look at a couple of examples. Here we have the point 1 square root 3 2 in rectangular coordinates. We want to convert this to spherical coordinates. So we need to use the x, y, and z values to come up with rho, theta, and phi. We can use this first equation to find rho since we know x, y, and z. Rho squared will equal 1 squared plus square root of 3 squared plus 2 squared. This will be 1 plus 3 plus 4, that'll equal 8. So rho squared is equal to 8. So be careful, this is rho squared, not rho, so we'll take the square root of both sides. So we'll use rho equals the square root of 8, which is 2 square root 2. Next, to find theta, we can use the equation here that tangent theta is equal to y over x. So tangent theta is going to equal square root 3 over 1. So that means that theta would be equal to arctangent square root 3 over 1. Now this ratio should remind us of a 30, 60, 90 right triangle. This angle here would have a tangent ratio of square root 3 over 1. That's going to be a 60-degree angle, or pi over 3 radians. And now we're left to find angle phi. So we can use this last equation here that states cosine phi is equal to z, which is 2, divided by the square root of x squared plus y squared plus z squared, which is the same as rho, and we found rho to be 2 square root 2. Well, this simplifies nicely. So if cosine phi is equal to 1 over square root 2, we know that phi is equal to arc cosine of 1 over the square root of 2. Well, this ratio should remind us of a 45, 45, 90 right triangle. So this angle here has a cosine ratio of 1 over square root 2, and that's a 45-degree angle, or pi over 4 radians. So the point 1 square root 3 2 in spherical coordinates would be 2 square root 2, theta was pi over 3, and phi was pi over 4. Now let's take a look at another example where we convert from spherical coordinates to rectangular coordinates. So here we're given rho, theta, and phi. So we have spherical coordinates and we want rectangular coordinates. Here are the equations that we can use to determine x, y, and z. Let's go ahead and work it out. X is going to equal rho times sine phi, so that'll be 3 times sine 3 pi over 4 times cosine theta, or cosine pi over 4. Let's go ahead and sketch these angles in standard position. 3 pi over 4 is going to be a 45-degree reference angle in the second quadrant. Here's our reference triangle for 3 pi over 4, and then pi over 4 is going to be the same reference triangle, but in the first quadrant. So x is going to equal 3 times the sine of 3 pi over 4 is going to be opposite over hypotenuse, or 1 over square root 2. The cosine of pi over 4 is going to be 1 over square root 2 as well. We're going to have 3 in the numerator, and square root 2 times square root 2 would give us 2. So here's our x coordinate. Now let's go ahead and see if we can determine the y coordinate. Y is going to equal rho times sine phi, so 3 times sine 3 pi over 4, times the sine of theta, or the sine of pi over 4. We can use these same reference triangles, so y is going to equal 3 over 1 times sine of 3 pi over 4 is going to be 1 over square root 2 again. We found that before. And now we have the sine of pi over 4, opposite over adjacent, 1 over square root 2. So it looks like the y coordinate is also 3/2. And now we're left to determine z. Z is going to equal rho times cosine phi, or 3 times cosine 3 pi over 4. It's going to give us 3 times the cosine of 3 pi over 4 is going to be negative 1 over square root 2. So it looks like we have negative 3 over the square root of 2. If we want to rationalize this, we can. We're going to have negative 3 square root 2 all over 2. Okay, so to put this all together, our rectangular coordinates will be 3/2 for x, 3/2 for y, and negative 3 square root 2 over 2. And because phi is more than 90 degrees, and that's the angle between this black segment here and the positive z-axis, it is going to be below the xy plane, as we see here. Okay, that's going to do it for the introduction to spherical coordinates. I hope you found this helpful.